Welcome to this session of vectors and tensors. It is the part of fluid dynamics course. I think we have to make fluid dynamics more enjoyable by understanding the physical concepts of mathematics. So, without understanding vectors and tensors, it is very difficult to digest the tough subject like fluid dynamics. But as soon as you understand the concept of tensors, it will be more enjoyable. You may fall in love with fluid dynamics. So we'll go to the next slide. Okay. Sometimes your idea will be complete by only a single number. Okay, how many pen you have or how many cars you have. The number itself give you the complete idea. But when you say this, another thing is that sometimes you say how much sugar you have, then one unit is necessary. But in vector, what is required? It should have some direction. Somebody asks you where is the shopping mall is, then you have to say this much 10 kilometers you go straight or go north and take 2 kilometer west and then go up in 10th floor or whatever maybe. So you should have this in 3D. You should have this three vectors, three unit vectors, three directions. So a vector consists of three direction and three-dimensional space. These things you have already understood from your school. But in later classes, maybe higher secondary or plus 1 and plus 2, you understand that a vector is should have not only unit and direction, magnitude and direction. It should have some other laws. It should obey some other law. So, for example, we studied that it should obey parallelogram law. And another thing is we coming to in this session you may understand that it is not only obeying a parallelogram law, but we should obey transformation law also. So we'll go to the next slide. Now we have to understand what is the physical concept of parallelogram law. Okay, you have given 100 grams fixed weight, 200 grams, 200 grams fixed weight, and you know that your unknown weight W is in lie between 100 and 200. So the idea is that with using these two stone, you can find out the weight of the unknown. How it is? It is, you can see that W is the vector sum of P and Q. So you know that all those things, root of P square plus Q square plus 2PQ cos theta. What I am trying to say, you should understand, you may be knowing all this formula and all, but at the same time you should understand the physical concept of vector addition. Okay, so we will go to the next slide. We have already said that it should obey parallelogram law or vector addition. But sometimes you have magnitude and direction, but it will not obey vector law. So vector addition law. So what is happening here is that even though it has magnitude, it has direction, but it does not obey or it should not obey this parallelogram law. So it cannot be called as a vector. So you take any book or some rectangular article, okay, then you mark that x-axis in that paper or something like that. You note this x. Then you rotate 90 degree about x-axis. That say you can see A is the vector in this. Then the magnitude is 90 degree. Okay. Then after that you rotate in a y direction 90 degree. Okay, that is B. B is perpendicular to A because A is the x-axis, is the rotation axis x, and B is rotation axis y. So you rotate about B again. Then you see that your book, the previous x-axis and transformed x-axis between, it is 90 degree. But actually here it says that the resultant of these two vectors should be aligned with 45 degree with x-axis. It's not so. It's not 45. It is 90 degree. So some things are not obeying vector's law cannot be called as vector. So fixed rotation is not a vector. But what we are doing here, what we are saying that it is, if it is very small rotation, very small like angular velocity and all, we consider as a vector, it behaves like a vector. But actually if you say fixed angle rotation is not at all a vector. Okay, then comes to the next law, transformation law. Before that we should understand what is transformation. Okay, so you see a vector A here, and if you multiply with any constant, the magnitude only changes. It will not change the direction. So you see vector B is in another direction. So how can we make this vector to a vector, to multiply with something, you should get the vector B. Okay, B equal to 1 square bracket multiplied by A. So what is this square bracket? See, A is, for example, it is I plus j, and B is 2I plus j. If you multiply with 2, then 2I plus 2j will come. Actually we don't need that. So you cannot multiply with constant to change the direction. So what we have to multiply? See, you can see A, B is 1, 2 in this right side matrix form. It is column matrix A, 1, 2. And another one is some square bracket, what I am trying to say, it is 1, 0, 0, 2, then 1, 1. So if you multiply this 1 into 1 plus 0 into 1, similarly 0 into 1 plus 2 into 1, you will get 1 and 2. So if you want to change the direction, you have to multiply with a transformation matrix or some kind of matrix. It has, see, the dimension is here is 2 by 1. Answer is 2 by 1. But the transformation matrix is 2 by 2. What it means, this fellow has 4 directions. Okay, we will come to later. First you understand that if you want to change one direction to another direction, you have to multiply with not constant, you have to multiply with some matrix, some array you have to multiply. Okay, you got it. That should be more than this dimension. This is 2 by 1 or okay 1 by 2 matrix. This is 2 by 2 matrix you have to multiply. So okay, so we should have some relation. That means we'll again go to the next slide for clarity of this concept. Okay, this is very important slide. Here you can see that one axis is 1 perpendicular to another axis, that is called 2. Instead of x and y I say 1 and 2, and another transformed axis is 1 dash and 2 dash. So for example, P is the vector, it is x1I plus x2j. I am not writing that, you say just x1 x2. And another axis system 1 dash and 2 dash, in that that point is x1 dash and x2 dash. So you can write that x1 dash by x2 dash equal to, you can see that bottom matrices, one matrix called C we say Cij into xi. So you can see just this one C11 C12 C21 C22. This may be some relation. Normally it is, you know that x1 dash equal to x1 cos theta plus y sin theta. No, that is x2 sin theta. So C11 C12 C21 C22 all are a function of theta. Maybe if you are rotating the axis, transforming to another axis with the angle of rotation theta, then this constants or these values all are function of theta. Whatever may be, there is a relation between x1 dash and x1. Okay, one axis system, one vector to another vector, you can express with a transformation matrix. So what I am trying to say here is that the transformation law is nothing but you should have some relation to represent the same vector in another transformed vector. Maybe it is a cylindrical axis, sometimes some another axis system, but you should have some relation. If there is no relation existing, then it is not a vector. That you should keep in mind. Okay, anyway, then we will come to the idea of tensor. Tensor is nothing but it is a linear transformation of a vector. Okay, you know that x1 dash as x2 dash is equal to some transformation matrix into x1 x2. So this transformation matrix, what it is, that this one is a linear transformation matrix. So this linear transformation is nothing but a tensor. Okay, got it? Okay, I will try to explain the next lecture with clarity. We'll take some example and all. Okay, so this how do you write it? You write this one x1 dash equal to, you can see, you just concentrate on the matrix multiplication in the right hand side, c11 into x1 plus c12 into x2. Similarly, this you can write that sigma, that 1 and 1 2, you can see that. So sigma is just summation, sigma c 1I into xi, where I is summation of 1 to 2. So you just expand, you will get that. Okay, so if in Einstein notation you should understand, is nothing but if you see a one time c1I xi, in that I is repeating. Wherever you repeat one indices, that means that it is just summation. So how many dimension is there, you just sum it. If in 2 dimension 1 to 2, if 3 dimension 1 to 3. Okay, so it should be c1I xi. Here I is repeated in single time. So that means this I is a dummy index. You can replace I 1 to 2 plus sum. That means c1 1 x1 plus c1 2 x2. Okay, if it is one more time is there, c1 3 into x3, like that. So in normally we will not write a sigma. So x1 dash equal to c1I xi, that is enough. So in this I is a dummy index, you put whatever k or something, k is repeating, means you can change 1 2 3. So c1k xk, then also meaning is not changing. Similarly, x2 dash also you can say c2I xi. Okay, same fashion, c2I xi. So I stands for 1 to 2. So you can replace that 2 1 with j. So wherever 2 is there, you can put j, but in everywhere j in single time is not repeating. That means it is not a summation, it is a free index. So j is a free index, that means x1 this much, x2 dash this much. So x2 dash equal to cji xi. Actually this should be written in no, lower script or upper script. Okay, so for I think it is clear, you can understand all those things. So what I am trying to give you an idea is that the tensor is not a big ghost or big fellow, not like that. It is very simple. It is a just in this presentation you understand, just it is a just a linear transformation of vector. It can be represented as a matrix. So and you know now Einstein notation. I will take this one in more detail in next lecture. Okay, thank you. Fine. Okay, I think in the last session we have understood that tensor is nothing but a transformation of vector. So what I am trying to say here is that I am not here to teach all the vector tensor analysis, etc., etc., but we should need some preliminary ideas about tensor. I am not teaching you vector, covector, covariance, variance. We are not going to that extent. But what we need in fluid dynamics, that we should study. Okay. So in the last lecture, last session, we know that tensor is a transformation of a vector. So we will go to one example so that you will get that idea more clear. Okay, in this slide you can see that one pendulum. It is fixed somewhere, and you can see force is acting downwards while it gets accelerated in the other direction, A. So we know that acceleration and force not in same direction. F equal to ma. So how can you get it? If you m is a constant, if you multiply with a vector A, the direction will not change. But if you want to change the direction, that M should be a second order tensor. So how the mathematics or concepts are developed? If you want to explain, you cannot explain with a constant. You should change into some other category. Okay, you call it as second order tensor. But in normal case, you see, in added mass concept in fluid dynamics, especially for those who deals with the ships and submarine and all, this added mass is not constant throughout all the direction. So if the ship moves in x direction, y direction, z direction and all, we have three different added masses. So in that case, we use a added mass matrix. So what I am trying to say here is that the mass itself may not be same in all directions, some cases. So in that case, we always use mass as a second order tensor. To understand the concept, I just given this. It may not be a actual thing, but you can get that idea, physical idea from this. Similarly, you can see there is one slanted cross section. Okay, so area is a vector. You may be knowing area is a vector with a normal on its direction, and force is always a vector. So in the second column, you can say that stress is force by area. So force equal to A into some sigma. This in square bracket I put it. Why? Force may not be same direction of the normal of the cross section. It may be slanted or it may be some other direction. In that case, that sigma should able to transform this vector into force direction. So in that case, we already know that this one is not a constant, it is a tensor quantity. So that's why sigma, we want to explain that. For that purpose, we can call it as sigma as a tensor. Okay, we just revised in the previous that tensor is a transformation of vector, and in this session also we have seen some examples. Now I think you must have got the concept of transformation of vector is a tensor idea. Another idea is that tensor can be expressed in a product of two vectors. In old style, we used to say, or in a school you must have studied, U vector is summation of Ui plus Vj plus Wk, where I, J, K are unit vectors. But you remember in the first lecture itself, instead of x and y axis, I put it 1 and 2 axis, and I say x1 and x2. I never say xy. So here also, the main idea is that this 1, 2, 3, we will add in as per Einstein summation convention, we just add it. So we use, instead of ijk, we use del 1, del 2, del 3 here like this. And u, v, w we never use. We say u1, u2, u3. So finally, u vector will be ui del I. As we know, in per one term, one indices is repeating. That means you have to add. How many dimension is there? You have to add from 1 to 3. u1 del 1 like that. u2 del 2 plus u3 del 3 like that. Similarly, if you take another one, it should be vj del j. Okay, so vj del j, again j is repeating, so you cannot use, if you are in a same dot product or vector operation, you should not use the same indice again. If it is ui del I already used, then you use vj del j. Okay, we'll go to the next slide. Okay, then here you can see u vector is, we normally use ui. Ui means u1 del 1 plus u2 del 2 plus u3 del 3. That already understood. Similarly, vj, we are supposed to say vj, then that also is v1 del 1, v2 del 2, v del 3. So when you multiply it, you have, instead of 3 terms, you have cross terms, that you have 9 terms are there. So ui vj, if you product it, one is vector, another is covector, we used to say like that. So if you multiply with that, you have one tensor with 9 components. One component is, you can see del 1 del 1, 2 del 3 del 3 last. So just like a matrix only, nothing great in that. So another concept is that first we said it is a transformation Okay, when it is transformed, then only we can call it as a vector. Similarly, a tensor is also a product of two vectors, and this tensor also should obey a transformation law. We are not going to that because that's some Cij Clk will come. Okay, leave it there. So what I am trying to say, if you want to transform one vector to a tensor, another vector, we need a tensor which have more than double dimension. Okay. Similarly, if you want to transform one tensor into another tensor, you should need fourth dimension. Okay. SoCijkl, like that is your matrix. Okay, we are not going to that. So okay, anyway, you should understand this much only. Another way is that tensor is a product of two vectors. In that case, it has same 9 directions. Cross direction also will come. Okay, thank you. We'll go to next slide. Yes, I forgot to say about rank or order of a tensor. We say scalars has no rank or no order, it will say 0 order. So vector we have rank 1 or order 1. And another second order tensor, third order tensor, all are called as a tensor only. But we normally deal with second order tensor only. It will be m by n. We have already seen 9 components will come in 3-dimensional space. But for our need for our cross product and other things, we have already seen only dot product we are coming to see in this lecture itself. But in later, we should know about a epsilon ijk1 third order tensor, alternating tensor. That is a very simple third order tensor. That only we need. But in our fluid dynamics, we can deal with all things we can deal with in second order tensor. So don't worry about higher order tensor. But nth order tensor is defined, and nth order dimension also is existing. And like that, we can mathematically we can derive everything. But no need to go that. So for our analysis, for our fluid dynamics studies, we need this much up to third order. Third order only this epsilon ijk only is required. Rest all things will come in second order tensor. Okay, fine. Okay, now we define one Kronecker delta. We already seen del I dot del j. What it will be there? So we know I dot I is only 1, I dot j is 0, I dot k is 0. Similarly, del I into del j dot del j is del ij. Okay. So del I dot del j, I forgot to write here, is equal to del ij. It is nothing but in diagonal terms only will come on. That is, whenever I equal to j, its value is 1. I dot I, j dot j, k dot k in our old format. So whenever I equal to j, its value is 1, otherwise 0. So del 1 1 equal to 1, del 2 2 also equal to 1, del 3 3 equal to 1. All other terms are 0. Okay. We'll go to next slide. Okay, in this new notation also, we should be able to get the dot product and cross product and all vector identities. So first we'll go, in this session, we'll see only dot product. See, in old case, u will be ui plus u2j plus u3k. V is u dot v1i, v2j, v3k. Then we will get dot product ui v1 into I dot I. Okay, all other things I dot j, I dot k, all are will be 0. Finally, you will come with u1 v1, u2 v2, u3 v3. Okay. Similarly, here you see vector u dot vector v means ui del I dot vj del j. Okay, then you group it. You take v here ui vj into del I dot del j. What is del I dot del j? It is nothing but del ij. What is the property of del ij? Del ij is value is a scalar. Okay, it's a value only. It's a del ij is not a vector because already it is a dot product. It is a scalar thing only. Two vectors by dot product, it will be a scalar. Okay, we'll come to that next slide. You will get more clarity in that. So del ij, what is the value of del ij? When I equal to j, its value is 1. Rest all cases it's 0. So you can write ui vj in that space where vi equal to j equal to 1. So ui vi you can write. Wherever j is there, that you can replace by I. Okay. So that only meaning, other all things terms are 0 as per this del ij condition. So ui vi del ij equal to 1. So no need to write. Ui vi is good. Then we know that ui vi is one indices repeating. Then we have to add it. Summation rule, Einstein convention. So just expand u1 v1 plus u2 v2, u3 v3. The same thing we got in previous notation also, previous style also. So why this is important means you can express all the terms in a single term, ui vi. That only required. So this is very easy. Dot product and all. No need to write entire matrix etc. Just write ui vi means it is understood. u1 v1 plus u2 v2 plus u3 v3. So we'll go to next slide. Okay. So now we see dot product between vector, tensors and vector. Here I want to say one small theory. It is nothing but it is a contraction. Contraction is nothing but reduction of total rank. Total rank will be reduced by 2 in dot product and reduced by 1 in vector product. That is cross product. Okay. So here tensor dot vector means tensor rank is 2, vector is 1. 2 plus 1 3, total rank is 3. Because of dot product it should reduce by 2. So resultant things value will be, rank will be 1. What is the rank value? What is the thing which has rank 1? It is vector. So tensor dot vector will be a vector. That is why sigma is a tensor. Dot with a you will get force. So how we will get sigma ij del I del j? We know that this sigma has two direction, del I del j, and you can say ak del k will be the area vector. So you take this a here, ak sigma ij, del I will be here, del j dot del k. So j equal to k, it has value is 1. Okay, so you can replace the all j by k or all k by j. So normally we'll replace k. Okay, sorry. So here it will be a is not k, a j sigma ij. K will not be there. You can replace all k by